Good morning, good afternoon, everyone, depending on where you're coming from. I hope you're all doing well. And thank you for joining us today for our webinar on Introduction to Composites Fatigue. Hopefully it'll be interesting and you'll learn something, whatever level you're coming at this from, whether you're a complete beginner or you know a lot about composites fatigue testing. My name's Dan Bailey. I'll just be hosting this today and answering any questions that you have as we go through. So if you haven't found already, there is a questions box where you can type in questions as we go, and I'll do my best to answer those as we go. And then if there's any outstanding towards the end, I'll open it up and we can go through some questions at the end as well, depending on how many we've got. I think that's about all. So I'm going to pass you over to our presenter today, who's Peter Bailey, and I'll hand it over to him now. Take it away.
Thanks very much, Dan. So as Dan says, I'm Pete Bailey, actually no relation to Dan. Anyway, I am the principal application specialist for Instron Dynamic Systems. In other words, I'm formerly a material scientist, a poacher turned gamekeeper or something like. So what I'm going to do is talk quite broadly today about composites fatigue and give you a bit of an overview. Excuse me, make sure my screen is keeping up. There we go. So in outline, I'm going to talk, well, first off, why on earth should you care about this? Why should you be interested in composites fatigue? And I'll talk a little bit about how it compares with working with metals. Now, I will apologize in advance. I'm going to make a few slight assumptions of some knowledge about materials testing in general and maybe a little bit of working with fatigue on metals. Please, if you do want to talk more about sort of some of the basic or common test types and test modes, we can talk at the end, or you can get in touch afterwards. After that, I'll talk a little bit about the sort of equipment that you need and how that might differ from metals testing equipment. And the thing that might be more interesting to those who've started this kind of work already is looking at improving reliability and removing some of the things which slow down your test throughput. So why should I care? Why should you care? Well, composites fatigue is actually quite a large-scale commercial test. There's a reasonable amount of capacity out there in the world, but demand is still growing. And I think there was a big rush to get into it a few years back, and then it slowed down a bit. But the growth in industry interest and industry need for that data is still ongoing. So who are those people who want that data? First and foremost, I think a lot of you will be very aware of how much importance the aerospace sector puts on composite materials, and really the majority of new commercial, well, I say commercial, also military aircraft, all major aerospace is really pushing to have very large proportion of composite materials in new aircraft designs. You should also be aware that in a slightly more perhaps futuristic sense, you've now got high temperature composites, so things like carbon-carbon composites are already being adopted now into turbine designs. And that's something that's happened a lot more quietly, I think. Also, quite topical is the matter of automotive structures. So high-end passenger vehicles have used composites for many years. Literally decades ago, Lotus cars used composite monocoque structures. But more recently, you look at things like BMW, especially with the i-Series, starting with the i3, the use of composites for a large proportion of the bodywork and the structure became a major point. More lower tier vehicles, there's been much slower growth, cars and commercials, but it is happening. The interesting thing, certainly I find this very interesting, is that with the really rapid development of fully electric vehicle designs now, composites are being adopted much more in much less of a replacement aspect, but embracing all those things of redesigning with the idea of we need to incorporate the batteries and the structure and using composites in the structure, and actually building those things together and getting the best out of everything in combination. Finally, much less glamorous, but it is that power generation and civil engineering. And quietly and unglamorously, they have really done the biggest amount of implementing composite materials and using fatigue data, especially that is wind turbines. So there's a huge install base worldwide, and they have been using composites fatigue data for a long while because it makes a genuine difference to the cost and the service life of their products. In the wider sense, you have obviously bridges, but you also have some of the more premium things like window fixtures for large buildings are moving to composites now, structural composites. So that's why and who's doing it. I'm just going to take a moment to kill a few myths, which I hope that not too many people hear these things now, but they've been rattling around out there for many, many years. So I'm going to say, no, this is untrue. First and foremost, composites don't suffer with fatigue. No, that's really, really not true. Experiments that came out in the late 90s, early 2000s, and I think it sprang from comments that the aerospace industry has made about using composites in a way where fatigue wasn't a problem, and that's to do with conservative design. But really, they absolutely suffer with fatigue. And from the earliest days of making high performance composites, so in the early 1980s, you will find published work on fatigue of composites. It's been understood for a long while. They're not commercially viable for high volume applications. Again, wrong. And I think that's really something that's been worked on very hard by researchers and by industrialization during the last 10 to 15 years. Really, we produce now far better material in a far more consistent production-facing way, commercial way. So that's not really a factor. Oh, but composites are so lightweight compared to their strength. We can just increase the safety factors and work around it that way. Well, aside from the fact that that's just lazy engineering, it's not quite true. Some of the other aspects mean that if you put on massive safety factors, aside from losing all the weight gain that you would achieve otherwise, you've also increased the cost massively. So that's not a good way to go. So, is it more complicated than working with metals? If I do composites fatigue, but I'm already doing something with metals. Well, the bad news is yes, it is more complicated, but it's not insurmountable. As I think I already mentioned, if you go into this with your eyes open, with some awareness of what you're dealing with, all of this can be managed. But you do need to think about machining, you need to think about specimen conditioning, you need to think about temperature, strain rate, and an effect that's particularly noticeable with composite materials, which is self-heating within the specimen. So to break these down a little bit, I'm going to start by looking about before you get as far as doing the test. Preparing the specimen is actually really important. Now, cutting it and machining it and polishing it, these are important things with metals, or with anything. Ultimately, the most important matter is that you produce a gauge section, that's the volume of material that you're going to really measure and test. You produce that without damaged surfaces or damaged edges. And that's true of metals as well, as I say. It is an aspect of composites do blunt machine tools fast. There's no two ways about it. and that they don't like aggressive cutting because you damage the edges of the material. Which leads me on to the aspect of specimen geometry. There are very, very well established specimen geometries for metals testing and for unreinforced plastics. And you know, our little icon there on the left hand side shows you that typical dog bone shape. But in truth, for composites testing, especially in fatigue, there is still a very large number of tests done using straight-sided, parallel-sided specimens, no wasted gauge section. There are issues with this. Simple applied physics tell you that there has to be a stress concentration at the jaw face. So where you clamp it, you're now applying a stress in 2 axes rather than just 1. And that will tend to force your failure up to the grips. It's not a nice thing, but it does, I suppose, on the positive side, it means that you will always end up with an underestimate. Your in-service material would always behave a little bit better. Now you can take measures to optimize the end tabs and to adjust the clamping force, and you can get that down so that if you are determined enough, it's really, really insignificant, but you can't remove that stress concentration. For that reason, if you actually go and look at some of the what I would call the most expert practitioners in composite fatigue, they actually use wasted specimens. They use a dog bone, a dumbbell-shaped specimen, and they have maybe not quite the same shape as a metal specimen, but it is wasted and it's carefully machined. And modern composite materials are really quite good quality, quite homogeneous. And there are companies who specialize in machining them. So you can set up and machine them without damaging, and get these kind of quite complex geometries. Sadly, that's not yet made it into major wording of standards, but that will come. That will come, and it has to. It really does need to for fatigue in particular. The final thing is material conditioning. Now, if you're used to working with metals, then really the only thing you need to worry about is, once I've made my specimen, keep it dry so that the surface doesn't corrode. Okay, so I'm exaggerating, but it's fairly straightforward. Your specimen can wait until you're ready for it. Now, with a composite, that's not altogether true. Polymers, water diffuses through polymers. There's no 2 ways about it. And certain types of them, particularly the matrix materials such as epoxy resins, they absolutely love water. They love absorbing water, and it does unpleasant things to their mechanical properties. So it really does matter whether I make my plate of composite, slice it up and test it within 2 days, or if I let it sit for 2 weeks in the lab waiting for me. You will change the performance of the material, you will change your test results. So you have to condition the specimens, whether that's by sitting them in a constant humidity chamber for an amount of time, or whether it's keeping them in completely dry conditions. You need to think about it. So, and one quick comment on that, the fatal mistake that people make is they put specimens in a plastic bag and think that will stop them absorbing water. And it doesn't. It will keep them clean, obviously, but an ordinary plastic bag does not stop water absorption. So, moving on to actually perhaps the interesting bit from Instron's viewpoint of when you come to do the test, 3 things to look out for. Temperature. So whatever you're going to use your composite for in the end, then you're going to have a temperature range that it's going to operate in. Now, even if you say it's only ever going to be room temperature, there's probably going to be maybe between 15 degrees C up to 30 degrees C. So you're going to see a 15 to 20 degree operating temperature range. You go to aggressive applications, then that's far bigger. Marine and automotive applications would routinely look for properties, specify properties between -30 plus 50 or minus 50 plus 70 degrees C. So you'll see, you're talking quite a big range here. But look at a typical composite material, and just 5 degrees C difference in test temperature is commonly enough to make a measurable impact on properties. So you do need to pay attention to that, whether it's at least measuring it or controlling it. So you do batches of tests at different temperatures. In a similar vein, strain rate. Now, it's for some metals tests, that's important, I agree. But when you look at high cycle fatigue and you're just doing very small elastic loading, the rule is usually do it as fast as you can. So metals fatigue, you would people commonly operate at 20, 40, 50 hertz test frequency. That is not something you can do for composites. Not only because the stiffness will actually be different at the different strain rate, but also because you're dissipating a lot more energy. And that energy is being dissipated as heat in the specimen. So I was just talking about 10, 20, 40, 50 degrees, 50 hertz, just at 5 hertz loading frequency on a fairly thin specimen of composite, you can get 20 degrees temperature increase. That's quite commonly observed when things go wrong. You try and avoid this, but it does happen. And I've got just as a little illustration, this is a thermal image sequence which I took several years back with typical straight-sided specimen. This is a woven carbon fiber reinforced material, something that you might see in an automotive body structure. It's the sort of thing that they use in the i3 and i5. And you can see just in the space of a few minutes, you've got 10 degrees temperature rise. And it is, once again, it's focusing, it's really being driven quite badly up near the grip, which you might think is strange since there's a great big lump of metal there, which would act as a heat sink. But your composite doesn't have great conductivity, and it does have this stress concentration. So it's heating there at the ends, worst of all. So enough about the difficulties. I'm going to come back to maybe some ways to address those at the end. Let's talk about just some basics of what equipment do you need if you're going to do some fatigue tests on composites. Well, firstly, you need some way to apply load. And if you're going to do that at a reasonable speed, you can't use a basic ball screw driven machine. You need a servo hydraulic actuator. That's a hydraulic piston with a servo valve control, or possibly a linear motor actuator. So that's a linear electric motor if you're doing fairly small specimens. You can see two basic machines that were made by Instron, a 100 kilonewton servo hydraulic and a 10 kilonewton electrodynamic machine there. So I've got a way to apply some force. I now need to put that force into the specimen. That means I need repeatable gripping, and I'll talk about that. What do I mean by that in a minute? But you do need to clamp it and do that in a nice repeatable fashion. And temperature control, as I've just been saying, we need to at the very least measure the temperature. You really do need to monitor it during the test for composites fatigue. But you might want to control it to do tests at, let's say, -30 room temperature and +70, for example. Other general requirements, well, you've got to hold that actuator, and those grips have got to be hung on something. So you have a load frame, and you want that to be fairly stiff. You don't want it to sort of wave around all over the place or experience compression during the test. But that's true of good quality metals fatigue as well. So practical software. Now, I know this sounds perhaps a little bit flippant, but in all seriousness, your biggest interaction with the test machine or this test is going to be setting up the test control and taking out the data. so you do need software which is reasonably sensible for that, and you do need it to be helpful, and you need to be happy to use it day in, day out. A couple of kind of comments at the end here. Optional things that you might want. They're not core to doing typical composites fatigue tests, but they can certainly expand your capacity, expand your capability nicely. One is strain measurement. That's as in the sense of direct strain measurement on the specimen, whether that's with video extensometer or a bonded strain gauge, or just a clip-on extensometer. The other thing that we see is very, very popular in machine purchases is the ability to what we call piggyback, to quick fit static test fixtures on top of those fatigue grips, so that you can pick up a little bit of capacity and maybe do some flexural tests, flexural static tests as well, or something, without completely demounting your fatigue load string. It just gives you a little bit of extra capability for the machine. So talking about capability and capacity, I do want to just address that briefly. I mean, one of the major benefits in materials and mechanical design terms, benefits for structural composites is that they have a high modulus and low density. So then a problem is that the specimen thickness is fixed. So that means that, you know, it's a high modulus, very stiff material, but you've fixed the size of your specimen. What do I mean by that? Well, large structures, particularly when you look at aerospace, you're making some fairly big structures here. You're going to need some fairly thick material. Now, yes, rolled metals do have structure effects in them, and microstructure effects in them, but those are nothing compared with the effect in a composite. Whether it's a continuous fiber material where you've got different plies, different layers with different directions of fiber, or it's an injection molded material, you still get alignment effects within that, within the thickness. And you do need to make your test specimen match the component as well as possible. So what that means is, if I have a component is going to be 20 layers thick, I have to make a specimen that's 20 layers thick. I can't scale it down. With a metal, then within reason, I just make a smaller diameter specimen. If I've only got a capacity of 50 kilonewtons force for my machine, I make this specimen small enough that will be enough. But with composites, that's not always possible. And what's that doing is that we often see machine specification is one size larger, effectively. So if you were setting up a lab and you might ordinarily, for metals work, think about a 100 kilonewton servo-hydraulic machine, you are very quickly thinking, oh, well, I'm going to do this. I'm expecting to take work in from Smith's Aerospace, not so that I'm not naming any major companies here, and I know that they make 1 centimeter thick composite plates. So okay, well, actually, I can't just work with 100. I need 250, maybe even 500 kilonewton load frame in order to do all of the work. Now, the price you tend to pay is that a larger actuator gives you less dynamic performance, or at least for the same, or at least it costs an awful lot more for the same to be moving as quickly. But you don't need that. As I've said, you're often down at only 5 Hertz test frequency, so that loss of dynamic performance is not a real penalty. But as I say, it does drive, this thickness effect does drive you to larger test frames and a little bit higher initial outlay. So on to, shall we say, the sharp end of things. Can I improve reliability or speed? And in terms of reliability, the rules are very similar to metals fatigue, or indeed for any good quality mechanical test. They're about good alignment, accurate loading, good specimen preparation. In terms of speed, well, for all the reasons I've already been discussing, that's a bit more challenging. But let's dig into those two things a little bit more. If we look at accurate loading, now, aside from obviously aspects of calibration and load cell accuracy and that sort of thing, when you look at a dynamic test, it's important that you tune your control system. Now, I'm not going to talk about this at length today. One of my colleagues did a really nice webinar a few weeks back, which you'll be able to replay. If you look at the Instron website, you will find a page of webinars, and all the ones we've recorded during this year, it can be replayed at your leisure. I would genuinely recommend, if you don't know much about dynamic systems, so fatigue test systems, that you do go and watch that one about tuning, because it's a really important effect. What you can see I've highlighted here just briefly is it's about getting you've set a target, which in this illustration would be those green dotted lines. If you don't tune right, then either it's going to take you a very long time to get up to your intended load level, or you're going to overload the specimen a little bit at the very start of the test, which is absolutely not the thing you want to do. So getting effective tuning is important to an accurate load. Accurate alignment. Now, this is how well you've clamped the specimen. This is I think this is going to be the topic of another webinar, not out there yet as far as I know. And it's about making sure you don't bend the specimen in any way when it's being gripped, when it's being clamped in the machine. Because you can imagine, if you're trying to do a straight tension test, then if you apply a slight bend to the specimen, you're not quite doing the same thing. So what do you need to get that accurate alignment? Well, you need precision gripping, and really that does need to be automated. Certainly for fatigue test systems, that takes you to hydraulic grips, or possibly pneumatic ones for very small specimens. You also need to be able to adjust the alignment of the load string and verify that, so measure the alignment. So this is, routine stuff for us. Very common features is we have some fixtures which get added into the load string, usually at point of manufacture, but we can add them later on, these adjustment features. We also have software and electronics, and you can see the rather nicely packaged specimen on the left-hand side there. That's a specimen with it'll have 12 strain gauges on it, which allow you to measure the deformation of that specimen when you clamp it in the grips, and then you can adjust from there. So again, not a topic I'm going to discuss at length today. But it is a really important thing for really any sort of test machine, but very much for fatigue, and something to be discussed at another time. Improving efficiency. So, as I've already said, composites fatigue, typically you end up running down at between 3 and 5 Hz test frequency, and that is slow. Now, how do we get around that? It means we need to manage this self-heating effect, this energy deposition effect in the specimen. So don't forget, every cycle, energy is going into the system, and that means there's energy being created, heat energy being generated inside the specimen, meaning your specimen temperature is not the same as your air temperature. You can't just put a temperature chamber around it and put a set point on that, and then just assume that your specimen temperature is the same as the thermal chamber setting. So composite fatigue tests are slow, as I say, and I mean, saying 8 weeks for a reasonable SN curve is optimistic, or perhaps generous for what you consider reasonable. So that's for maybe 12 or between 12 and 16 points. which is it's not the most highly detailed SN curve that you're ever going to get. So what are you going to do? Do you want to run at higher frequency? Well, as we've said, no, that's a bad idea. The other aspect is that test temperature fluctuates severely. So highly loaded specimens will have a high temperature increase. Very lightly loaded specimens, actually, you don't really get much of a measurable increase in surface temperature. So what do? Do you run at even lower frequency, just to allow that heat time to dissipate? Well, you've got this tension between these two things, and they're clearly incompatible. However, all is not lost. There are approaches to frequency adjustment, basically, but some of the basic solutions that people use to include forced cooling of the specimen. You will go to labs and see, it's not terribly uncommon to see forced cooling. Someone has literally put a small fan in front of the specimen. They're using air blast cooling across the specimen to keep it from getting too hot. Now, yes, absolutely, it's a very pragmatic solution, but it does generate a through thickness temperature gradient in your specimen, which really any material scientist is going to tell you that's not a good idea. That's not what we want. The other thing you can do is monitor the temperature and pause intermittently for cooling. It does work, absolutely, but honestly, the time reduction is minimal because you heat the specimen so quickly, and then you have to wait for almost as much time as you've saved for waiting for it to cool down every few minutes. Now, there is an approach to adaptive frequency, and Instron, we've actually packaged that up and we've made a fully automated solution. Our name for it is Specimen Self-Heating Control. And what it does is continuously monitor the specimen temperature and modulate the test frequency. And what it allows us to do is actually keep the specimen temperature stable during the test. And I would say that typically for a fairly long fatigue test, we could keep the temperature stable just by modulating frequency, stable to about plus or minus half a degree. That's a degree centigrade, by the way, which is really, really good and really not something you'd see without some sort of temperature control stabilization. What it means is you don't overheat highly stressed specimens, even in their short fatigue life, and it means that you can really gain some time with those less loaded specimens where you're going out to millions of cycles. Little case study. We've done several case studies on this, to prove to ourselves and as much as anything that we're not introducing something unpleasant in an effect on the results. You can see here that you really do get very, very similar results. You can see the SN curve on the right-hand side there. That's peak stress up the vertical axis and number of cycles. So 1,000, 10,000, 100,000 going across the bottom there. The red crosses are with the specimen self-heating control, the adaptive frequency. The blue diamonds are a fixed 4 Hertz frequency. So we worked with a professional composites fatigue lab to do this. Their basic test protocol is to use 4 Hertz fixed frequency. The interesting thing, depending on how carefully you look, is that the adaptive frequency actually can reduce scatter in the fatigue life. Now, it's not something we would say is always the case, but it can be an added benefit. And if you look at what's happened during the test, from our 4 Hertz, at the very highest load level, you've taken a little bit off the frequency, and at going down to the lowest loading level, you've added just over 50% to the frequency. So it's not a drastic change in frequency. You're not going to need to worry, in my opinion, you don't need to worry about the change in strain rate because it's only very small. But you can see there's very little difference in time for those highly loaded specimens, but you haven't overheated. And at the other end, where you're out to you're looking at 2, 3, 4 million cycles. That's a lot of hours for one specimen, and you've taken 30% off that almost. Really does make a good improvement. So, a nod to some other productivity features in terms of tuning, making that simple and effective, and above all user-friendly. Tuning a dynamic system is not a trivial matter, but we've got some really good tools, one of which is stiffness-based tuning, and that's an Instron patented method. Means that you've got a really simple way that you can optimize your tuning for every single specimen. As I say, you want to know about that, go and look at the webinar by my colleague Jonathan Phillips from a few weeks back. Embedding calculations. So we're collecting data throughout the test. That means that, especially with modern computing power, you can do calculations on all those signals you're bringing in for every cycle, and you're basically calculating live. That means that you can do a dynamic modulus measurement and record that right the way through the test. It's going to save you time post-test analysis if you have a customer for your data who wants that modulus drop measurement. Equally, you can pause for inspection if you see more than a certain proportional drop, and you can. Something that's not commonly implemented yet but it is out there, is defining specimen failure as a proportional drop in stiffness, and so you can do that automatically in this case. Last of all, I mean, it's in some ways slightly a small thing, but it does help. It allows integrating control of a temperature chamber if you want to do temperature tests, is to look at the controlling the temperature chamber setting from the test software. Now I'm nearly at the end, and just to emphasize, I've seen a couple of raised hands there. We'd love your questions, but we're going to come back to them at the end as an easier way to manage this. So a few words about the expanding scope of composites fatigue. So as I say, for quite a long time, the real thrust of that work was always straight coupons and fairly simple specimens. And really, the big one was carbon fiber and glass fiber with epoxy or vinyl esters, thermosetting resins. So, and that was the biggest driver for that was absolutely the wind turbine industry. Recent developments in materials and processing have brought thermoplastic composites into focus. So you've got the carbon fiber PEEK type materials, which are produced by tape placement. You can see a little illustration of a robot here. I think that one is produced by Coriolis. That's a real strong interest these days for the aerospace structures. So you've got that aspect of things, but you've also got injection molded materials for secondary structures. So I mean, this is an illustration of a prototype part that was being looked at for, I think it was aircraft door hinges, but equally secondary structures in automotive are really taking that on as well, and that's one of the easiest wins for them is secondary structures for automotive. But you've got multi-axial fatigue as well, is something that was I think historically was considered hard, and it was. There's no two ways about it. Multi-axis fatigue and loading is hard to do well on composites. But you've got both, but you've really got some very direct applications for automotive. And you can see the large picture on the right-hand side of the screen there. That's a set of hydraulic grips specifically designed for combined axial and torsion test on tubes, on composite tubes. And you can imagine where that might come up in automotive. Quite simply in drive shafts and that sort of thing is the biggest application. But you've also got sort of suspension straps and that sort of things. Multi-axial fatigue is important because multi-axis stresses do change materials properties. Doing that stuff at materials research level is still hard, as I say, but pragmatically it's quite important on tubes and even component level stuff. So this is really something. This is perhaps some of the wider growth in peripheral areas of composites fatigue over recent years. So I'm going to wrap up there and say, in conclusion, composites fatigue is practical and achievable as long as you've got good equipment and you spend just a little bit of time to understand what's going on. It's a significant test market out there, not least because throughput is never as fast as for metals, even though there's perhaps the market for it is, the data is still growing. You do need to look out for that understanding of materials is important to remember, that anisotropy for composites, those temperature and strain rate effects, and it's a really diverse market. So I would always encourage you to plan ahead. It's something we have some great conversations with people about, understanding what they're doing today, but also where it might take them in the next few years. So I'm going to finish there, and thank you for your attention. And I think Dan is going to manage our questions for us.
Yeah, thanks very much, Pete. We've had a couple come in during, so yeah, let's just get on to those and see if we can answer them here. Anything we can't answer here, we will get back to any of you after the webinar as well. So the first one is the average strain rate from a heating control mode test the same as the strain rate from a fixed mode 4 Hertz test?
The average strain rate, well, no, because if you, I'll just scroll back up to there. There we go. So if you think about it, the fixed frequency at 4 Hertz it does actually give you a different strain rate across the different loadings. So the 4 Hertz fixed frequency test is not a fixed strain rate. Our test is also not a fixed strain rate. Sometimes, now I have, this is a slightly weird question. It's in certain circumstances, it can give you a more stable strain rate, but not completely consistent. One of the aspects is that this is probably a discussion for another day. Happy to take this offline. Is if you look at some of the data that's out there, there are stages during a composites fatigue test where it undergoes much more heat deposition than others. So actually, you get to, in some cases, it might be 3/4 of the way through the test. You start to get a level of damage accumulation, and the heating rate actually increases. So you have to reduce. There's a whole range of interaction between the temperature and the strain rate and the heating rate. So the simple answer is no, the strain rate is not constant, but neither is it constant when you do a fixed frequency test.
Perfect. Right. Thank you for that. And then there's another one here, which is saying, are sample fixtures like a split capstan grip good for testing fatigue on non-tabbed single ply continuous fiber composites that are flexible enough to bend around the grip?
Well, I mean, it's a good suggestion. I have discussed that with people in the past, but I've never seen anyone actually implement it. So what we're talking about here is a capstan grip. So we're talking about a thin filament that will bend round, and you've got a wide radius load in it, and it's tension only grip. My caution on that would be actually about fretting and sort of frictional damage at that end loading point. I'd be fascinated. I'd be happy to discuss that with you. It's not something we routinely have demand for, but happy to take that offline if people are interested.
Okay. We'll just do one more. There's a couple more coming, but we'll just do this as the last one, and then anything else we haven't answered, we will get back to you after the webinar. And I think there's an option to even ask questions in the next 24 hours anyway. I think that will come through as an option for you once you finish the webinar. So this one, I think I know the answer, but I'll let you explain it just to confirm. But can you explain a bit more how the Instron machine achieves automatic frequency adjustment upon a temperature rise? Is it possible to program this accordingly?
Okay, well, right. What we do is we need a feedback reading, a measurement from the specimen temperature. Ultimately, the software doesn't care how it gets that, as long as you generate a channel. Initially, what you provide the software with is your target test temperature, which should always be just slightly above the surrounding temperature, whether that's the lab temperature or the chamber temperature that you're working with. The first thing that the software does is it starts with whatever frequency you've given it to start with. So you ordinarily you'd give it a sensible frequency, maybe 3 Hertz, and it will wait for the specimen to be wait for that to run for a number of seconds. You can adjust that stabilization time. If you've got a very responsive temperature sensor, very responsive specimen, you can keep that time window short. If you've got a very noisy signal or a very sluggish, thick specimen, you can lengthen that time window out. What it'll do is the system looks at the start of the test. It says, well, I'm trying to get to that temperature. How's the temperature rise looking? That temperature rise is going up really steeply. The first thing it will do is wind the frequency back down very quickly. The last thing we want to do is overheat the specimen. And then if it's not heating up very quickly, by contrast, it will take a little step, increase the frequency, little step, increase the frequency, until you start to see some temperature rise. Then as you get close to the target for the specimen, it will allow that to equilibrate. Once you're in a stable state, it will monitor it, and if the temperature starts to rise, once again, it will do quite a responsive reduction in frequency, taking the sorry, I'm getting a bit of echo here. Taking the idea that overheating is very bad. Similarly, if the temperature starts to drop off because it's actually getting into a more stable state, then it will increase it. So it really is just there's an algorithm which gets you up to specimen temperature, and then once you're in a steady state, then you have a similar sort of command versus feedback error kind of system. It's not PID, it's not like that, but there are similarities in how it behaves.
Great.
Sorry if that wasn't very clear, slight distraction in the middle there.
That's okay. So thank you very much for that, Pete. We'll call an end there. There's a couple of other comments that we will get back to outside of this webinar. So thank you very much, everyone, for attending. And you will also see a recording of this webinar appear on the Instron website in the coming days, probably early next week. Okay, thanks very much, everyone. Goodbye.
Thank you very much. Have a nice day.